So in this lecture, we're going to be talking about the photoelectron spectrum that you have been looking at in the chem activity. And you're going to be looking at a PES to identify the atom by determining the electron configuration by reading it. And what a PES does is that specifically it can show the energy levels and the energy sublevel that the atom's electrons can occupy. And we can use that to deduce what the electron configuration is. So let's go ahead and look at this sample one here on this slide. And you can see here that they talk about on the y-axis the relative number of electrons. And these numbers on the x-axis refer to what the AP exam, what they call the binding energy. And I'm going to go ahead and write that down. Binding energy, which is how much energy it takes to remove that specific electron from that sublevel. It's similar to, but not exactly the same thing as ionization energy, because ionization energy refers to the amount of energy it takes to remove the outermost electron, aka the valence electron, where binding energy can refer to however much energy there is to remove a particular electron from a particular sublevel. So when you read these, you can see here that there are small numbers, and then there's a little bit bigger one, and an even bigger one, and then a really big one up here. So the scale is distorted a bit. This is from 0 to 10, and 10 to 100, and 100 to 500. And the units can be something like megavolts or joules, or whatever they use to designate what the how they measure the energy, but we don't have to worry about it right here. So the first one what you can imagine here is that if you look at any particular atom, the electrons that are closest to the nucleus are going to be experiencing the greater Coulombic attraction with the nucleus. So those would understandably have the greatest binding energy. So the one we should pay attention to first would be this one right here, because that's got the highest number down here on the bottom, okay, 126. And that implies that those are closer to the nucleus because of the really high binding energy, which means that it is a very small amount of potential energy. You could say it's negative, a really large negative value. And so that has the greatest binding energy as a result. So this would be the electron from the 1s sublevel. Then moving on, the next energy level we should be concerned with would be the second highest number, which actually is the one over here. Okay? And there's 2 electrons, which would make sense because that would be in the 2s sublevel. Then beyond that, it would be here the 2p sublevel. And then we move on up to one more energy level. And then this one would be the one with the lowest binding energy, which would be the valence electron of that particular atom, 3s. So we can then go ahead and write the electron configuration as 1s2, 2s2, 2p6, 3s2, and we can use that to identify what element that would be. So if you look at the periodic table, that should be the magnesium PES that we're looking at. Okay, so why don't you go ahead and try this example. So pause the video and go ahead and try this one. Okay, so if you did that correctly, you would have gotten this electron configuration, and you would have identified the element as being aluminum. Okay, so now we should be able to try to work backwards, and you want to create the electron configuration for chlorine, and make the PES. So why don't you go ahead and first go ahead and write the electron configuration for chlorine. So pause the video and look at your periodic table and see if you can write that electron configuration. So this is what you should have gotten, and I put here a periodic table for quick reference. We have 1s2, 2s2, 2p6, 3s2, and 3p5. Now, I'm going to go ahead and draw up the PES based on that electron configuration, and it doesn't have to be especially beautiful or anything. You just need to indicate the relative amounts. And the way they do it on the AP exam is that they actually have the higher binding energies over here. Higher, I'll call it BE for binding energy, and lower BE. And the y-axis, you can label as either intensity, okay, or you can call it the frequency of electrons, number of electrons, etc. Okay, so the 1s2, we're going to go ahead and make this peak like that. That would be 1s2. And then 2s2, you want to make that the same size as the other one, the same height. Okay, but 2p6, you want to be triple the height of the first two because it's 2p6. So that's going to go all the way up to about maybe like right here. Again, you can just ballpark it. And then 3s2. And then 3p5 should be a little bit shorter than the 2p6 one. And that would be the PES for chlorine. And when you look at this, just make sure you understand that we're only asking for relative heights, so that one height should be 3 times the other one, but it doesn't have to be exact. You can put a scale there if you want to, but it's not necessary at all. Okay, just note that the AP exam, they just do the high on this side and then the low on this side, where the ones that we did earlier happen to have a switch. And you can do it either way as long as you specify where the ionization or binding energy is increasing. And you can also say that over here, in binding energy increases this way. Okay, so now let's go ahead and talk on the next slide about how to analyze the PES and what kind of inferences you can make about it. Okay, so let's go ahead and read this question. Is more energy required to remove an electron from the 1s orbital of argon or chlorine? So I'd like you to pause the video for a few moments and look at argon and chlorine and where they're located on the periodic table, and draw upon your understanding of what we've been doing with the chem activities to see if you can come up with a reason. So let's pause the video. All right, so here is the reasoning that I came up with. And this is the language that you want to be able to use on the AP exam in the free response when they ask you these kind of explanation questions. So I said that the distance between the nucleus and the 1s electron in argon and chlorine are approximately, not exactly, but approximately equal. So in the Coulombic attraction equation, you're holding the denominator, the distance, constant. And now we're going to be looking at the numerator, which is talking about the charges. And the core charge of argon, due to the extra proton that it has, see, argon's located right here, and chlorine's right here. Because it has an extra proton, it has a greater core charge as a result. And the core charge is +8, chlorine is +7. So that increases the Coulombic attraction between the nucleus and the 1s electron. And that means that more energy is required to remove that one. Okay, so you need to really say in the Coulombic equation, you need to say what is being held constant and what is changing. And it's a good idea to use terms like approximately to give yourself some wiggle room. Okay, so now let's go on to the next question right here. would it take less than 0.9 millijoule per mole, 0.9 millijoule per mole, or greater than 0.9 millijoule per mole to remove a 2s electron from the boron positive ion? And explain, and they give you the ionization energy for beryllium. So go ahead and take a look at the periodic table, and go ahead and see if you can come up with your own explanation, and then pause the video. Okay, so this was similar to the last one. If you look at the periodic table, beryllium atom has 4 electrons right here, where the boron atom has 5 electrons. But the B plus would have 4 electrons because the positive charge indicates that it lost an electron. Okay, and by the way, the term we use between B plus and BE, which is 4 electrons, we call them isoelectronic. Same number of electrons. Okay, they're different species, but they have the same number of electrons. And so in this case, you want to reference Coulombic attraction as always. The distance between the nucleus and the 2s energy level is approximately the same, but boron has a core charge. The boron ion has a core charge of +3, while the beryllium atom has a core charge of +2. So that greater effective nuclear charge, core charge, means that the Coulombic attraction is greater, and it's going to require more than 0.9 megajoule per mole to remove that same electron. Okay? All right. So one more thinking question. How would the PES for the sodium ion and neon be the same, and how would they differ? So let's pause that for a moment, and we can see if we can answer that. So both of these have 10 electrons, and again, you want to make use of that word isoelectronic, and which means the PES will look the same in terms of the number of peaks, because they're both going to have the same height and the same number of peaks because they have the same electron configuration. But remember that the sodium has 1 more proton than neon does, and as a result, the binding energy of Na plus would be greater. And that's going to shift all of the peaks to a higher binding energy number on the PES. Okay, and I think it's going to take some moments here to be a good idea to write down what the core charges of both of these are. Neon has a core charge of +8. Okay, because neon has 10 proton minus, you take away the 2 core electron, and that's going to give you the +8. Okay, sodium positive, it can have a core charge of +9. Okay, because sodium has 11 proton, but the sodium ion has 2 inner electron to give you a +9 core charge. Okay, and you remember the chem activity stated the core charge is equal to the number of valence electron, but that's only for a neutral atom. So for an ion, you really need to think about the number of protons minus the number of inner shell electrons to give you the overall core charge. So again, because of sodium's higher core charge, that's going to lead to a greater binding energy between that and the electron. Okay, so that's it for this lecture.